Good morning, everyone, and welcome to Pak Abdurro'uf to day 7 of IVC, Introduction to Astrophysical Modeling and Computation. Today we have two sessions in the morning. Each of session is 90 minutes, and these are a hands-on session. And for session 1 will be interactive, and also session 2, I think. Session 1 will be interactive after about 20 minutes presentation from Pak Abdurro'uf. So please feel free to ask questions after his presentation. Okay, Pak Abdurro'uf, time is yours. Thank you.
Okay, thank you. Good morning, everyone. I'm very excited to be here and talking to you about James Webb Space Telescope. First of all, I want to thank the organizer for giving me these invitations, this opportunity to share to you about James Webb Space Telescope, or we usually call it JWST. I hope you can see my screen. Can you see my screen? Can anyone confirm that you can see my screen well? Okay. And hear my voice? Okay, then, yeah, first of all, I would like to thank the organizer for inviting me. I'm very happy today to talk to you about the James Webb Space Telescope, or we usually call it JWST, and make a hand-on tutorial on the data analysis. My name is Abdurro'uf. I'm a postdoctoral researcher working on galaxy evolution. So I'm studying the evolution of galaxy across cosmic time, studying galaxy at various redshift, and study the evolution across cosmic time. I have recently completed my postdoctoral contract at ACAA, Academia Sinica Institute of Astronomy and Astrophysics in Taiwan. And now I'm about to start my second postdoc position at the Johns Hopkins University, and closely working with my new supervisor group at the Space Telescope Science Institute in Baltimore, USA. Meanwhile, now I'm actually on a vacation in Indonesia for a few weeks before leaving for US. I feel very excited to move to Johns Hopkins University and Space Telescope Science Institute, because it's where the JWST is being operated. Here's my plan for this lecture. First, I will briefly introduce the James Webb Space Telescope, how it works, how its capabilities, and what the science goals that are going to be achieved with this telescope. Then we will do twice hands-on tutorial on JWST data. First, we will be using simulated near-cam imaging data from the SEARS survey. And in the second tutorial, we will be using real JWST data on the SMAX 0723 cluster that was publicly released last month as part of the early release observations. Finally, there will be a quiz at the end of my lecture today. Now let's start from a brief introduction to JWST. JWST is the successor to Hubble Space Telescope, and it works in the infrared wavelength. In this short introduction, we will learn about the goals and strength of this JWST telescope. Why does it need to be placed into the space, and why does it specialize in infrared wavelength? And lastly, we will learn about the instrument on board of the JWST. I will begin with this movie of cosmological simulation to explain what are the science questions that motivated us to build a large telescope like JWST. What I'm showing you with this movie is a computer simulation of a small chunk of the universe that evolved from immediately after the Big Bang until the present day. This simulation includes gravity, pressure, black holes, star formation, and the stretching and expansion of the space. The running time is shown in the bottom left corner here. What you see is the universe taking shape over billions of years. Each bright node in this movie is galaxy. So each bright node is galaxy. The galaxies have a variety of shape and sizes. You see this galaxy forming and colliding under the influence of gravity. They interacting with each other, pulling each other with gravity. Merger are commonly happen at high redshift, and that's transform the galaxy morphology. You will start seeing this galaxy light up as new stars form and explode. You can also see some explosion due to the feedback from the supermassive black hole that are residing at the center of the galaxy. So the key question that we are going to answer is, how did the universe evolve from a homogeneous soup of gas and dark matter into the galaxy, star, and planet as we found in the present day universe? So what was the universe like after the Big Bang, and what are the characteristic of galaxy as the universe evolved over billions of years? Then as gas cool, as gas cool in this galaxy, star will eventually form. And so how do these stars form, live, and die in the galaxy? And finally, what kind of planet are formed around these stars? So those are the scientific questions that motivated us to build a large telescope like JWST. And JWST is one of NASA Great Space Telescope program. It stands on the shoulders of the previous Great Space observatories that NASA have launched. So why do we launch telescope into the space? The reason is that the Earth atmosphere blocks some specific spectral wavelengths, such as X-ray, gamma rays, and ultraviolet. The gases in the atmospheres also can block or absorb most of the infrared spectrum. So for light that does reach the ground, the Earth atmosphere can cause a blurring effect to the object image, which we call it as the seeing effect. So to capture more light from distant object and avoid from the blurring effect or seeing effect, we must send telescope to the space. And equip that with a specialist instrument. So starting in the 90s, NASA launched a series of space-based telescope. Hubble Space Telescope was launched in 1990, and it is still operating until today. And Chandra Telescope at Chandra Space Observatory was launched in 1999, and it is also still operating today. And its work mostly on the X-ray. It's specialized in X-ray part of the spectrum. And Spitzer was launched in 2003, and it's operating until 2020. So 2 years ago, it was finished. So Spitzer specialized in infrared, but with the lower spatial resolution compared to JWST. So JWST was launched on December 25 last year. It's designed to orbit the suns at Lagrange point L2, which is a stable orbit that is around 1.5 million kilometers away from Earth. The main reason for placing JWST at L2 in orbit around suns at L2 is that it makes the JWST stay in line with the Earth and allows the sun shield to protect the telescope from the light and heat from the suns, Earth, and Moon. This is very important because as an infrared telescope, JWST should be kept at very low temperature. In fact, it should be operated at a temperature of minus 225 degrees Celsius to be able to perform as expected. JWST has 3 key features that make it revolutionary. First is the size of its mirror, primary mirror. This is one of the most important characteristic of telescope, because a bigger primary mirror can collect more light, so it can see fine distant object in finer detail. The diameter of the JWST primary mirror is 6.5 meter, while Hubble Space Telescope was only 2.4 meter. This means that the light collecting area of the JWST is over 7 times larger than that of the HST. This allows us to see very fine object in the universe, very far away galaxy. The second key feature of JWST is its sophisticated instrument. So JWST carries not only imaging capabilities, but also spectroscopic capabilities that will allow us to get spectra of distant objects like galaxies, stars, and planets. By looking at the spectra, we can learn more things than using only imaging data. So by taking spectra, we can learn about the chemical compositions, surface temperature, and kinematics of objects like galaxies, stars, and planets. The third major strength of JWST is the fact that this work on infrared wavelength. Unlike HST, which observe ultraviolet, optical, and near infrared, JWST specializes in collecting infrared light. This is one of the strengths of the JWST. Why observing in infrared light? With the infrared view, it allows us to peer through the dense cloud of gas and dust into the formation site of the stars. As we can see from this figure, the image in the top was taken with Hubble Space Telescope, while the figure in the middle and bottom panel were taken with the JWST near-infrared camera and mid-infrared instrument. In the JWST image, we can see many newborn stars that were not visible in the Hubble Space Telescope image. This is because of the obscuration by the dust. So in the Hubble image, because Hubble view ultraviolet, optical, and near infrared, which are obscured by dust. So we cannot see newborn stars in the Hubble image, while we can see them in the near-cam and MIRI image from the JWST, because they are specialized, they observe in infrared, and infrared can peer through the gas and gas cloud. And by observing in infrared, JWST is also capable of capturing light of distant object that has been redshifted by the expansion of the universe. So due to the expansion of the universe, the light from distant objects are redshifted so significantly, such that the observed wavelength, the observed light is become infrared. With the JWST sensitivity in infrared, it can capture light of distant object very efficiently. Next, let's look at the instrument on board of the JWST. JWST has 4 instruments: MIRI, NIRCam, NIRSPEC, and NIRIS. I will explain briefly each of them. The mid-infrared instrument, or MIRI, provide imaging and spectroscopy capabilities in the mid-infrared. It has 4 components: camera, spectrograph, coronagraph, and integral field unit instrument. And its operating wavelength is in mid-infrared from 4.9 micron to 28.8 micron. There are 3 modes of imaging imaging observation that we can do using MIRI. First is the standard imaging and coronographic imaging, and time series imaging. And there are 4 spectroscopic modes that can be done using MIRI. First is the single slit spectroscopy mode that we can slit spectroscopy, integral field unit spectroscopy, and time series spectroscopy. The second instrument is near-infrared camera, or NIRCam. Also, this instrument also provides imaging and spectroscopy capabilities. It has three components: camera, spectrograph, and coronagraph. And yeah, its operating wavelength is from 0.6 micron to 5 micron, so it's near cam. It's in near infrared. It has three imaging modes: standard imaging, coronographic imaging, and time series imaging. And it has two spectroscopy modes: wide field slitless spectroscopy and time series spectroscopy. The third instrument is the spectroscopic instrument called NIRSPEC, near infrared spectroscopy. This is a versatile tool for near infrared spectroscopy. It has three components: spectrograph, microshutter array, and integral field unit. Its operating wavelength is the same as NIRCam, which is in near infrared. So from 0.6 micron to 5 micron. There are four spectroscopy modes that we can do using NIRSPEC, including slit spectroscopy, multi-object spectroscopy, integral field spectroscopy, and time series spectroscopy. So it doesn't provide imaging capability, unlike the previous two instrument. The fourth instrument on board of JWST is called NIRIS, near infrared imaging and slitless spectrograph, or this instrument provide imaging and spectroscopy capabilities. It has three components: camera, spectrograph, and aperture mask. Its operating wavelength is the same as NIRCam and NIRSPEC, which is in near infrared. So from 0.6 micron to 5 micron. Micron mean micrometer. It can do two imaging modes: standard imaging and aperture mask interferometry. And there are two spectroscopic modes that can be done using this instrument, including wide field slitless spectroscopy and single slit spectroscopy. And now, how does JWST conduct scientific observations? There are four types of observing program done using JWST. First is called early release observations. This is the first observation conducted immediately after the end of the commissioning process. The purpose of this observation is to demonstrate the full capabilities of JWST. And this early release observation has been done, and the data, full color data, were published last month for the first time. And the second type of observations is Director Discretionary Early Release Science Program, or DDERS. This is the observation program to be executed within the first 5 months after the commissioning end. And so it's been starting now. So it's already started and it's ongoing. And it will the data will be immediately released to the public, I guess, starting from the end of this year. The guaranteed time observations, this is the third type of the observing program of JWST. This type of observing program is intended to be led by members of the instrument and telescope science team. So those people who contributed significantly to the development of JWST will get this observing time. So all these three observation program were not open to the general astronomy community. Only the last type of the observing program, which is called General Observer Program, is open to the astronomy community. So this is our opportunity to propose something to JWST and get peer review, selected, and executed. The cycle one already done, so there are already many programs that have been selected for the cycle one, or the first year of JWST. The second year or cycle two opening of proposal will be open in November. So be prepared for that. If you are if you want to observe something using JWST, and please prepare for the cycle one opening of the proposals in November. Last month, we have seen the release of full color image from the early release observation AERO program. There were 5 targets observed in this early observation to showcase the full capabilities of the JWST. First target was the galaxy cluster SMAX 0723. This is the first deep image taken with the JWST and has already become the deepest ever image taken by humanity, surpassing the extreme Hubble deep field taken with the Hubble Space Telescope. Although with the very much shorter observing time. Yeah, it's only 12 hours compared to 25 days with HST. Within this image, the gravitational field of the cluster magnifies the light of background galaxy through the effect of gravitational lensing. We also see many galaxies show a gravitational lensing arc in this field, which are galaxies that are stretched by the strong gravitational field. The second target that was observed in the AERO observation was the Southern Ring Nebula. This target was observed using NIRCam and MIRI instrument. This nebula saw the end stage of the evolution of star, like our sun, which become white dwarf and has set its outer layer and stopped burning fuel through nuclear fusion. Those outer layers now form the ejected cell. The third target was Cosmic Cliff in the Carina Nebula. It's a star-forming region in the Carina Nebula. Most of this region was previously hidden in the Hubble image due to the obscuration by the thick dust cloud. Now it can reveal with the infrared image with JWST. The third target that was observed was the exoplanet WAPS 96b. They have managed to get the transmission spectrum of this exoplanet. The transmission spectrum is obtained by comparing starlight as filtered through the exoplanet atmosphere when the planet moves across the star, compared to the unfiltered starlight detected when the exoplanet beside the sun, beside the star. The transmission spectrum indicates the presence of the water vapors. The last target that was observed in the AERO program was the interacting galaxy called Stephan Quintet, group of interacting galaxy called Stephan Quintet. This mosaic of NIRCam and MIRI image is the largest image mosaic from JWST until now. It is composed of around 1,000 separate image files and that were made into a single mosaic. This image gives a close view of how interaction among galaxies can affect evolution of the galaxy, something that was supposed to be common frequently at high redshift or early cosmic history. This figure shows a comparison between the image taken with the JWST and HST. The image have been almost perfectly aligned so that we can do these comparisons. From this comparison, so this is SST, and this is the image taken with the JWST. From this comparison, we can see clearly that JWST image are sharper and can capture fine galaxy that were previously not visible with the HST. With the high spatial resolution of JWST image, we can start to see the morphology of the galaxy that were seen as a blob in the HST image. So this remarkable imaging with JWST will certainly revolutionize the field of galaxy evolution. This image is just the beginning. There will be many more exciting results to come in the next few decades with JWST. So if you are not involved in any JWST program in cycle 1, that's okay. You can still get chance to work on the JWST data because several JWST program in cycle 1 will release their data to the public. Some of the program have already got their data and they are working on analyzing the data. And in the next few months, they will release their data to the public. What we can do now is to prepare ourselves for the incoming data by learning the data characteristic, having science goal in mind, having plan, and also preparing our analysis pipeline, which we will learn in our tutorials today. Some of the major survey in cycle 1 that will release their data to the public are the following. SEARS, the Cosmic Evolution Early Release Survey. You can see their website if you want to know more about this survey. The survey will cover around 100 square arc minute of the EGS field. This is the Hubble field, with NIRCam, MIRI, and NIRSpec. The second program called Class JWST, you can visit their website here to know more about this survey. So this survey will observe lensing cluster Abell 2744 using NIRSpec, NIRIS, and NIRCam. These two program have already started, and many papers have come out from this survey on archive. If you are interested, you can see archive listing in the last 3 weeks or so to find their very interesting papers. And in the next few months, they will release their data to the public. And the last program that I want to highlight here is called Cosmos Web. This is the largest JWST program in the cycle 1. So it will observe around 0.6 square degree of the sky. This is comparable to around 3 full moon area. So they will observe using NIRCam and MIRI. So be prepared for the incoming flux of JWST data in the coming year. I'm currently involved in 2 GO JWST programs that are led by my current supervisor, Professor Danko from Space Telescope Science Institute in Baltimore, USA. In this JWST program, we will study gravitational lens high-redshift galaxy in the WHL cluster, the WHL 0137 and MAX 0647. Interestingly, we will also study the most distant star we call Arendelle in this sunrise arc galaxy. This red arc is actually a galaxy that is stretched significantly by the strong gravitational lensing. Because it's stretched, so everything inside is resolved. And fortunately, we managed to find a star, individual star. This galaxy is located around 6.2, and so this is the farthest star ever observed until now. There was a paper on this from our team published in Nature earlier this year. The graduate student from JHU who found this star give name to this Arendelle. Arendelle is taken from Old English, which means rising sun, rising star. That's all my presentation for introducing the JWST. And now let's start to the tutorial. But I guess I will give a few minutes for a question in case any of you have some questions before we move to hands-on tutorial. Any questions? If no, then we can move to hands-on tutorial immediately. Oh, someone raised hand, so please unmute yourself and ask your question.
So that was a nice introduction. So when you were telling about the JWST different instruments, you talked about this an IFU instrument, right?
Yeah.
So what I know, is it the same IFU technique which is used in Muse BLT, if you're familiar?
Yeah, as far as I know, that's similar. Yeah, similar technique adopted by Muse instrument. So slicing the image. Yeah. Okay. Any other questions? One more questions?
Yeah. So in this also, JWST also, we are getting a cube as Muse gives, right? Not just an image, just a 3D cube, right?
3D cube as well. So there are many observing mode, as I said. So for imaging mode, we only have imaging data, but for other mode like integral field spectroscopy observation, we will get 3D cube of data. Yeah, there are many observing modes in JWST.
Okay, thank you.
Okay, if no more questions, then let's move to hands-on tutorials. So I intended to make my hands-on tutorial as interactive as possible. If you have any questions pop up in your mind, just don't hesitate to interrupt me anytime. So the all of my tutorials are written in Python and are uploaded already. I have already uploaded the material to my GitHub page. I think someone have shared that in the slides, and hopefully hopefully you have had chance to download the data or just look at the GitHub page to learn some things about the tutorial that I'm going to deliver today. So let's move to the GitHub page. So this is the GitHub page that I have specifically prepared for this hands-on tutorials. So this is my own GitHub page. If you have a GitHub account and want to follow, you're free to follow. And yeah, hands-on tutorial on JWST data analysis for the International Virtual Course on Astronomy IT Institute Technology Bandung 2022. So what we will learn from these tutorials are the following. So first, this is actually a basic analysis using basic analysis we can do using imaging data. Doing aperture PSF matching of multiband imaging data. So commonly we from observation we get data in multiple bands. And using multiple bands, we can construct the SED of galaxy. So it's very important to observe astronomical object in multiple bands so that we can get the SED of the galaxy. But before we can get the SED of the galaxy, we need to do several steps that we are going to do today. First is the point spread functions of imaging data across multiple bands. So imaging data from multiple bands have different PSF size. Usually a shorter wavelength have a higher spatial resolution compared to the longer wavelength image. So in case of JWST data, near-cam image have higher spatial resolution or PSF, smaller PSF size compared to the MIRI image, which is in mid-infrared. So point spread function is actually spatial resolution. So how light spread on the image. And yeah, secondly, we will learn how to create a beautiful color RGB image from the multiband imaging data, and then detection and source extraction of astronomical object in an image. So we will detect astronomical image in the astronomical object galaxy, especially galaxy in the image field. And we will do aperture photometry. So for those objects that are detected in our field, we will do aperture photometry to measure flux across multiple bands and get the SED of the galaxy. And we also do photometric redshift measurements because mostly we will have imaging data spectroscopy doing, although JWST have on board sophisticated spectroscopy spectrograph, but a spectroscopy observation is usually very expensive. It's very time consuming. So most of the time we will have only imaging data in multiple bands in NIRCam or MIRI. And previously from HST, we can also combine all of them together to get the photometric SED. And yeah, one of the very important informations we can infer from the galaxy, we need from the galaxy is the redshift. How far is this galaxy? And from the redshift, we can also see the look back time to that galaxy. So when that galaxy was emitting light, what age of the universe when those galaxies emitting light. And yeah, using redshift and observing galaxy at various redshift from very low redshift 0, up to redshift, for example, redshift 5, we can learn the evolution of the galaxy. So redshift information is the basic information that is very important for studying galaxy evolution and also cosmology in general. Performing SED fitting for measuring stellar population properties of galaxies. And after getting redshift, we can perform SED fitting. This is a process of comparing our observed SED with the model SED to infer the underlying properties of the stellar population in the galaxy, like the metallicity, age, mass, star formation rate, and so on from the SED fittings. And optional, if we have times, we can go further with dissecting spatially resolved properties of galaxy with PixFit. This is the software that I made in the last few years. I specialize in analyzing the resolved SED of galaxy, not only the integrated SED, but we can resolve the galaxy, get the SED in each pixel level, and do SED fitting in the pixel level and get the properties in the pixel level. So we can get the maps of the, instead of global properties of galaxy, we can get the maps of the properties, like map of star formation rate, stellar mass, metallicity, age, and so on. So this is the data source that we are going to analyze. So first is the simulated JWST near-cam imaging data from the SEERS survey, Cosmic Evolution Early Release Science. This is one of the survey in the DDERS. So this survey has been started in late July, I think, and many papers have come out from this survey. If you are interested to read their papers, you can go to archive and see the listing in the last few weeks, and you can find very interesting papers. Many of them are discovery of high Z galaxy from the SEERS observations. But in the next few, we have to prepare for this incoming data from SEERS. Since SEERS has not released their data yet, but they have shared their simulated data. So we can, instead of working on the real JWST data, which is not available right now, we can start working using the simulated data. And what I mean by working here is to prepare our analysis pipeline before the coming of the data. And yeah, so we will be using this, we will be using the data from them. Oh, so the data can be found here, the data release from SEERS and simulated data release 3. And yeah, unfortunately, because of the limited times of our allocated hands-on tutorial, so we will be only analyzing near-cam imaging data, not spectroscopic data from NIRSpec or others. So we will use this updated near-cam imaging from SEERS. You can download the data from this or from my Google Drive. So someone raised hand, Hawari. Can you unmute yourself and ask your questions?
Yeah, I'm sorry, Dr. Abdurro'uf. Should we see your presentation materials or your another screen? Because we still see your presentation materials.
Oh, still. Oh, sorry. Thank you very much for letting me know. So I'm not aware of that. I thought I have moved to GitHub page. Thank you for letting me know. So this is what I was pointing at. So now can you see GitHub page?
Yes, we can see your GitHub
Okay,
page.
okay, thank you. Thank you for letting me know. Yeah, so this, and secondly, we will work on the real JWST data. So this is the only real JWST data that we have currently. This real JWST data was released last month from the ERO observations. There were 5 targets observed in the ERO, but we will only analyze one of them now. So SMAX 0723 cluster. And unfortunately, the data was very raw data. The data that was published by NASA was very raw, and we need to process using the JWST pipeline to make it in the FITS file format as as HST imaging data. But fortunately, there were already several process data available on the public. One of them is produced by Gabriel Brammer from University of Copenhagen in Denmark, using his Grizzly pipeline. So it was the data is publicly available here. And for the preparations, you need to install these dependencies, software dependencies, to be able to run the Jupyter Notebook. So my tutorial are in Jupyter Notebooks and written in Python and work on Linux. And Python 3.5 or later. And basic Python package for astronomy like NumPy, AstroPy, Matplotlib, SciPy, PySAO. These are very easy to be installed. I think you can use PIP or Conda to install them. I don't need to explain more on how to install this. I think you can learn that from their website. Photometric analysis package like PhotoUtil, SEP, and PhotoUtil is very great package for photometry in astronomy, in case you haven't known this. There are many functions available in PhotoUtil that you can use for photometric analysis of imaging data in multiple bands. And there is also SEP. This is the source extractor, the Sextractor, the very famous software Sextractor, written in the Python version of Sextractor. These packages are also easy to be installed. Please follow the installation procedure in their website. And the photometric SED tool, EAZ, made by Gabriel Brammer. This is also very cool software for photometric redshift measurement. This is very easy to be installed, as the name suggests, easy. And it's specialized in the photometric redshift measurement, but not for SED fittings. So it's very fast. It can process around 1,000 galaxy in a few minutes. Please follow the installation instruction in the easy GitHub page or its older website here. Documentation in PDF file is also available here. So to install, actually, you just need to run one command called make command. So just download using git clone, put in your desired directory and decompress and go to the SRC directory and execute this make command. And that's all. But you need to prepare several files to execute easy. I will explain more later in my tutorials. SED fitting tool called PixFit. This is my own software. I'm very proud of this. I've developed this in the last few years, and it's just finished last month, and I have just released to the public last month. This has been used in a few papers already, and yeah, this is specialized in SED fittings, especially the SED fitting on spatially resolved scale, in the pixel scale. The installation procedure is a bit complicated, but I guess, but I hope you can follow the instruction in the installation page here. And the next step is downloading the required data. So you can clone this repository in your local computer. The issue is that and it's also a rise in the Slack, is that the data size is very huge. Yeah, it's indeed, because JWST data is of course very huge, because it contains millions of pixels. So the resolution is very high, the pixel scale is very small. So even though the sky observed, the area of the sky that is observed is very small, but because the pixel size is very small, so we have millions of pixels within it. So it's increased the file size. So the file size is very huge. Actually, I'm running my tutorial on the server. So I hope you have access to server and work on the analysis on the server. But if you don't have currently, you can just follow the tutorials, and you can always look back at these tutorials materials, and when you have time later after these tutorials, and work on the JWST data. And yeah, so first you need to download the PSF matching kernels. I have put this in my Google Drive link here. And then you need to move that kernel into the kernel directory here. And then the second is the data from SEERS. You can either download this from the Google Drive link here, or from the original web page from the SEERS website. And then the next data that we need is the ERO data SMAX 0723. So we will use JWST and HST imaging data. So you can use download SH script that I have provided inside this data directory. This is the script. You can run this script on the terminal, and it will download the data automatically and put inside the data directory. And yeah, once you have downloaded the data, you can go through the tutorials, and this is the convenient way of going through the tutorials in this order. First, we will be working on the NIRCam simulated data from SEERS. So it's always easy to start from the simulated data than from the real data. Can prepare ourselves, our science goal, and analysis pipeline, building on our analysis pipeline using the simulated data, and preparing for the incoming of the real data from the JWST in the next couple of weeks, next couple of months. And yeah, there are two directories. The SEERS directory is intended for working on the SEERS simulated data, and ERO SMAX 0723 is intended for working on the ERO data, real JWST data. And yeah, let's go to the Jupyter Notebook one by one. Yeah, in this first step, you can find it here. I think if you haven't downloaded this, you can actually open this online. So this is a good thing about the Jupyter Notebook and GitHub is that we can, but we need strong, strong internet connection to open this. Sorry for that. And yeah, let's go. Let's look at the step 1 in the Jupyter Notebook. So in this step, we will be checking the simulated NIRCam image, make some crop, and perform point spread function matching, and create a nice color RGB image. The simulated NIRCam image are taken from Sears, as I have said. So there are 6 filters provided by Sears, and these 6 filters also will be observed by Sears. So only 6. And F115, 150W, 200W, 277W, 356W, and 444W. So if you are curious about the filters in the NIRCam instrument, you can look at the website of JWST. So filters. So what is filter? Filter is the like the name. So it's filter out the part of the spectrum that we are interested in. So so this is the NIRCam filters. We will be using this white, W mean white filters. So actually NIRCam have many more filters, the medium filters, very wide filters, and narrow band filters. But we are going to working with the wide filters. So, and 6 filters. So using filters, we can measure flux at particular wavelength. Yeah. And yeah, there's the filters of the NIRCam. And yeah, first we list the filters and their names, and this is a arbitrary name I made. So, and our input image are listed here. So science image and error image. These are the data that we downloaded from the Sears website. So these are provided by the Sears survey. Science means science image. This is the background subtracted image. This is the intensity image. We can measure flux using this image later. And the error image is the estimate of the error or uncertainty in pixel level. We will use this to get the estimate of the flux uncertainty later. And checking image and cropping. Yeah, it's always very helpful to have a glance on the appearance of the image before we start working on it. So yeah, this is the way we can do to show the image using Python. So we can use fits. I guess you all have familiar with this kind of package, AstroPy. And to open fits file, you can use fits functions inside the astropy.io, and you can, yeah. And yeah, this is the image that we will working on. So each single point here mostly are galaxy, but some of them are stars, bright stars, foreground stars in the Milky Way. And because the image are not well mosaic, so they are not all connected. So I decided to do a cropping. So I will work on 2 cropping. First is this crop region, and the second will be this one. So first we will crop this image. You can use you can define the boundary of the crop, and then yeah. This is just to make sure that our crop is not outside of the image boundary. And as we can see, they are within the image boundary. So we have the data inside of our crop. And yeah, we can use these functions from AstroPy to crop fits file data. And this, what's nice about this function is that we can retain the WCS informations, world coordinate system information inside the header. So in the header, we always have WCS information. This is the information that we can use to convert from the Cartesian coordinate into the SCI coordinates, right ascension and declinations. And this function, even though it's a making cut of the fits file, but it retained the WCS informations within in the new cutout image. This is beside cutting out the image, we will also calculate the variance image. Variance image is just the square of the uncertainty image. So taking the square, so to get the data, we can use the astropy.fits to get the data of the 2D array of data from the fits file, HTU the data, and then for calculating variance image, just taking the square of this cutout data and make a new file. We call it crop one. I just put crop one name in front of the old name, just for simplicity. And this is our crop image. So this is this image portions. So we crop, so we get this. Yeah, this is in log scale. Yeah, NP log 10. So all those pixels that are not detected or having a negative value, they are not appear in this plot. But the source of galaxy, they commonly have a positive value, so they appear on the image. And this is the variance image in 6 filters. And now we do a cropping for the second regions. Do the same. We do the same process as previously, and this is just to make sure that our crop area is not beyond the imaging data. So they are within the imaging data. We have the data inside our crop, and we again use these functions from AstroPy to do cropping, and this is our crop image. Okay. The next step, we will do PSF matching. This is the process of homogenizing the spatial resolution of imaging data in multiple bands. So as I said, imaging data in short wavelength usually have a higher spatial resolution compared to the imaging data in longer wavelength. Yeah, to know the PSF size of the NIRCam data, you can visit this this website. Sorry. So the PSF size of NIRCam filters or NIRCam camera are varies across the filters. So it has a strong size or high spatial resolution in the shorter wavelength, and coarse or low spatial resolution in the longer wavelength. Yeah, this is the PSF size as function of wavelength in the NIRCam. So in the shorter wavelength, it's very good and high spatial resolution, so 0.03 arc second. While in the longest wavelength, 5 micron, the spatial resolution of the PSF size is very big. This is comparable to HST, 0.17 arcsecond or so. So before we do any analysis with the imaging data, like doing aperture photometry or measuring aperture flux of the distant galaxy, we need to do a point spread function matching. We get rid of this difference in the spatial resolution. We homogenize the spatial resolution of all the imaging data. So what commonly we do PSF matching by calculating the kernel. We have model PSF or either model PSF or empirical PSF, and then from this PSF we can calculate the convolution kernels. There is a nice review about the PSF matching process in this FOTUTIL website, and FOTUTIL does provide very helpful many functions for the PSF matching. So as I said, FOTUTIL is very good package for doing photometry in astronomy. And yeah, model PSF or we will use kernel from this website, Princeton website by Tran Lee, and the technique for producing this kernel was explained in this paper. And this is the kernel for matching PSF of F115W to F444W. As I said before, the longest wavelength have a larger PSF size. So what we want to do here is to transform all the PSF size from the shorter wavelength imaging data to the longest wavelength, so F444W. So we will blur, in the other word, blur their image to have the similar spatial resolution as the F444W. So we can use this function to do the convolutions from the AstroPy. And before we can do a convolution, we need to transform the kernel size to have the same pixel size as the imaging data. We can use resize PSF from the AstroPy, from the FOTUTIL package. And so the native pixel size of the kernel can be get from the header using this line. And we resize the kernel pixel size into the same pixel size of the image. So the imaging data pixel size is 0.03 arcsecond. This is the native pixel size of JWST. And and do this convolve FFT to do the PSF matching, and we do this to both the science image and the variance image. And we make a new fetch file and put PSF match in front of the name of our previous image for simplicity. So now we have more data inside our directory after executing those commands. So crop 1, crop 2, PSF match, crop 1 after the PSF matchings. And our disk space will be occupied more after we run some commands. So be prepared for the disk as well, other than the memory, the RAM memory. And this is image after PSF matching. For the crop 1 regions, and we also do this the same procedure to crop region 2 using the same functions, convolve FFT, resize PSF for resizing the pixel size of the kernels before convolutions. And this is the result of the PSF matching to the crop region 2. And after this, all the imaging data in 6 filter have the same pixel size and the spatial resolution, or PSR size. So yeah, they all having the same spatial resolution. So after this process, we can then proceed to further analysis, like aperture photometry, and here we will make RGB color image. Yeah, this is to provide us with a visual impression of the image, because in the original image in single filter, we only have bright and dim region, so black and white, or here yellow and green. But using RGB image, we can have a visual impression of the image. So this is the combination of three filters. So I use F115. This is centered at around 1.15 micrometer, and this is centered at around 2 micrometer, and this image center at around 4 micrometers. We can use this function to make the beautiful RGB color image, just to following this step or line of codes, and we can get this kind of nice color image. This is also what we saw from the ERO data that were published by NASA last month. So that the process are the same. So they did the PSF matching, spatial resampling, and combine three filters together to make the RGB image. But this is the simulated image. So and in this simulated image, the galaxy are very round. So they are just a STScI models. So elliptical STScI model that are planted in this field. So we don't see spiral or nice structure galaxy, but instead we only see STScI models, elliptical STScI models, because this is simulated image. We can do the same procedure to crop region 2. Yeah, like this. Yeah, this is not special for JWST data. You can also do this kind of analysis to other imaging data like HST or imaging data from ground-based telescope. If you have multiple filters, imaging in multiple filters. The second step. Any questions for this first step before we continue to the second step? Sorry. If no, then yeah, let's move to a second step. In the second step, we will do a source detection and aperture photometry for crop region 1. We will do this separately from crop region 1 and crop region 2. So as we see from the previous image, we saw many galaxies inside them, but we will not do detection manually by eyes, like placing circle on the field manually, but because that will consume our time and it's not very not efficient. Instead, we can use some software to do source detections to detect some galaxy within the field. Here for example, we can use SEP, which we will use in this tutorial. We'll do all of the process using SSP, which is a Python version of Sextractor. Our goal here is to produce the photometric catalog. So our goal is to detect all the source within the field and do aperture photometry to measure the flux in multiple bands and produce the catalog of object within the field. And from this catalog, we can proceed with many analysis like SCD fittings, for example, SCD fittings to measure their properties, the properties of the galaxy in the field. First, we list the input image among the set of filters. So this is the process image the image that we have processed from the first step. So after PSF matching, after cropping, and after PSF matching. If you remember, I put the unique name in front of the original image to indicate the step. So after cropping, I gave a crop, and after PSF matching, I gave this PSF match name. So this all science image and variance image have been PSF matched. And we do source detection instructions using SEP. You can run this using this, SEP. There are many useful functions in SEP, but we only use few of them here. So if you are interested in learning more about SEP, which is very useful for photometry analysis of imaging data, you can go to the SEP website. So I put the link throughout my tutorials. So you can always go back to the tutorials in later time and do a more detailed learning later after this tutorial. And yeah, we will use SEP extract functions. This is the input of these functions. So the data science, as I said, we can use feeds from AstroPy to extract the 2D data from the imaging data and input this into these functions. And we set the detection threshold. We use to we will do the detection on this particular filters, so 150W filters. We can also do this to other filters actually among one of the 6 filters available. And this is the error data. Error is the square root of the variance data. And threshold, detection threshold is the threshold above which, if the galaxy have this have a value above this threshold, they will be detected as source. That's the meaning of the detection threshold. And this is the keyword for the blending. And you can learn more from the SEP website. And we will also produce the segmentation map. So after running this function, we we will get the detected sources. Those detected sources are stored in this array. So object and segmap. Segmap is for segmentation map, while the object contains the astrometry of the detected object. So we can get the number of the object. We got 488 galaxy within this field detected by the SEP. We can show the detected object on top of the image. For example, we draw the detected object on top of the F150W image. So all those objects that are that have ellipse aperture on top of them, they are detected object. So, but SEP cannot differentiate between stars and galaxy. This is the disadvantage or the weakness of this software. So, and in my tutorial, I haven't had chance to deal with this stars and galaxy separations. So as we can see here, this is a star. This is stars with diffraction spike, and this one are stars. This also stars. But yeah, this will contaminate our catalog later. I haven't made the assignment yet, but if you are interested to do assignment, you can use this as a first assignment. So separating stars from the galaxy in the image, do automatically, and yeah. And the segmentation map. SAP also produced segmentation map. This is the basically the membership of pixels. So pixels that have similar value are belong to the same object. So for this object, all the pixels have the same value. This value are the index of the object detected by the SEP. So we have 488 galaxies. So we have highest index of 488. So the highest index here is 488. So this is the region of the detected object. And we can do aperture photometry to measure the, Pak Irfan Hakim, do you have any questions or something?
Yeah, we still have about 15 minutes more.
Okay, yeah. I think I will use all of the time for the first session for tutorials, and for the second session, I will end before 15 minutes for quiz. But yeah, I will end in 9:30 here.
Okay, thank you.
Yeah, thank you. So next we do the aperture photometry to get SED of detected object. And yeah, we also use SAP here using this sum circle. So we this work by placing circle with the radius that we can set. Here we set a radius of 10 pixels. And so, yeah, it will make a circle around the center of the detected object with the desired radius. This is the 10 pixels, and the SCP will sum up the flux of pixels within this circular aperture to get the estimate of the total flux. And yeah, you can just follow this line of code. And yeah, the flux and flux error are stored in this array, outputted by the SCP. And yeah, and then we can make a table. We can use AstroPy table like this. And yeah, these are the total flux measured, and these are the coordinate of the galaxy X and Y coordinates within the field. So we have 488, but because in the Python, usually the index starts from 0, so we have the highest index of 487, and X and Y central coordinates, and this is the flux in 115W, flux error in 115W, and so on. So we have flux and flux error in 6 filters, and yeah, that's our the SED. Yeah, SED is spectral energy distribution is simply the flux measured at various filters. And we can convert those flux. Oh yeah, the output the output is still in the original flux unit of the JWST image. So the original flux unit of JWST image is megajansky per steradian. And from this, we can convert this into Jansky or AB magnitude using this kind of using this formula. Steradian is this area. So we will convert the flux into microjansky, and this function this unit, erg per second per centimeter per angstrom. This is flux density per unit of frequency, and this one is flux density per unit of wavelength. And we also convert the flux into AB magnitude using these functions. This is the basic function in photometry. I think you all familiar with this. And yeah, you can we can estimate the magnitude error from the flux error using this this formula. And once we got all of them, we can make a SED plot like this. So SED, as I said, is the flux measured at various filters. So SED of some of the galaxies. So I choose this randomly. So 20. Yeah, I throw a random integer 20, and yeah. These are random objects within our field, and then we want to make we are going to make a photometric catalog. So this is basically a catalog that contains the coordinates of the galaxy and the measured flux in various filters. Yeah, And yeah, it's always useful to have the coordinate in right adjacent and declination, or the sky coordinate, instead of the Cartesian coordinate, because yeah, in area and deck we can this is the I mean this is the general general astronomy coordinate. Everyone will know this coordinate instead of the X and Y, which is very specific to a given image. And yeah, we will store in this catalog in text file. This is the way to store data into text file. Yeah, I also included that into my GitHub page, so you can check. So this is the photometric catalog we produce. So yeah, we will end this first round of the tutorial and at 9:30 and continue the tutorial after break. Yeah, and yeah, because we and in the next step, which I will explain after the break, we will do a photometric redshift using AIZY. Before we can use AIZY, we need to make a photometric catalog as an input to the AIZ software. So it has a specific requirement for the input, and you can the input shape or format is like this. You can just follow this, and I also have included that in my GitHub page. So yeah, that's the first step in any analysis of the imaging data. So we do PSF matching, and yeah, homogenizing the spatial resolution of multiband imaging data, and do aperture photometry, and we even do creating a nice color image from 3 filters. Yeah, that's all for the first session of my tutorials. We will continue again in the next session. Thank you. In case you have some questions, we still have 7 minutes for questions. Oh yeah, that step 2 was only for crop region 1, but yeah, the analysis for the crop region 2 is given in the separate Jupyter notebook, but actually they are the same step. Same step. Possible of one more possible assignment is to try another aperture here for the SEP, for the aperture photometry with SEP. So I use some circle. So this is a circular aperture, but SEP also provide elliptical aperture. And yeah, next assignment will be try another aperture for the for calculating flux using ellipse aperture, and try Cron radius instead of the circular radius. Cron radius is roughly the whole radius of the galaxy. And we can have a better estimate of the total flux using Cron radius instead of simple circular aperture. So that's second assignment if you are interested to do that. And another note is that the easy software require the flux to be in microjansky unit. So yeah, so that's why we convert the flux into microjansky from megajansky per steradian. Megajansky per steradian is unit of surface brightness, but microjansky and erg per second per square centimeter per angstrom is unit of flux density. Jansky is flux density per unit of frequency, while this is the flux density per unit of wavelength. So that's why we include the wavelength into the calculations. But AB magnitude is more is converted from the flux density per unit of frequency. Yeah, I think that's all for these sessions, and we'll continue again in next sessions with the photometric redshift measurement and also working on the real JWST data from the early release observations. Yeah, thank you. So we'll have a break for 30 minutes, I think.
Yeah. Thank you, Pak Abdurro'uf. We have a short break, about 15 minutes, right?
15 minutes.
It's a precious time to all participants to trying analyzing this data image. I think very interesting. Thank you again, and please give applause to Pak Abdurro'uf. Okay, thank you. We'll meet again after 15 minutes.